Okay, hi everyone. My name is Ron Petrick. I'm an associate professor at Heriot-Watt University in Edinburgh. Um, Today I'm going to be talking to you about using epistemic planning for task-based human-robot interaction, at least for the first hour. And then for the second hour, Mary Ellen Foster from Glasgow University is going to take over and talk about social interaction with robots. So I want to start today by giving you a little background about me and about this topic. I do have the chat going, and so if you have questions, comments, just put them in the chat. The stream seems to be about 20 seconds delayed, so if I don't get to the question immediately, I will try to when I see it. So first of all, hello from Edinburgh. Here's a beauty shot of Edinburgh on a nice sunny day. It's not sunny today, it's raining, but you get the sense of the city where I'm located. Um, I'm an associate professor at Heriot-Watt University, which is one of three universities in Edinburgh. And we mostly focus on technical work, so things like engineering, computer science, physical sciences. And I'm part of a center called the Edinburgh Centre for Robotics that has a strong focus on developing robotic systems and autonomous systems. And in the bottom of the screen here, you see some examples of some of the robots that we have available in the center. So a little bit of background on me. I've said a couple times an associate professor. I'm also the director of the Automated Planning Lab, which is really the focus of my research. I'm also in charge of the master's program in computer science in artificial intelligence. I coordinate a few efforts within the planning research community. And I was a visiting professor at Sapienza last spring, and I helped Luca teach the human robot interaction course. So you may have seen me wandering around the department, or possibly you sat in on one of my talks. My research is in the area of automated planning, and in particular, kind of three aspects which I've listed here. So first of all, how can artificial agents decide what behaviors to use to achieve their goals? And so I look at things like epistemic planning, which will be the topic of today's talk, temporal planning, task and mission planning, things like multi-agent planning. I'm also interested in how agents represent and reason about their beliefs, so knowledge representation. How can they use this information to act or to interact with other agents in the world? And then finally, an area called cognitive robotics. How do we actually take some of these abilities, these higher level cognitive abilities, and actually put them onto robot systems or artificial agents? And here I do work on in areas like human robot interaction, collaborative robotics, explainability, and actually executing these robot systems in domains in the real world. So here's an example of some robot systems that I've worked on various projects. So the one here on the first one, the top, this is an industrial robot system. It's used in a automotive factory, Peugeot in France, and we looked at ways of automating parts of the factory process, the assembly process, using robots to collect parts and deliver them to the assembly line. Um, the other image on the top here is a project I'm working on right now called the Orca Hub. And here we're looking at robots to be used in support of the energy sector. So this might be robots that are able to work on oil rigs or scan um, various tidal fields, monitor solar energy, whatever it is, and different types of robot platforms. So drones, underwater robots, surface robots. Um, On the bottom here, I'm also interested in explainability or instruction giving. So how can we get robots to give instructions to humans in a way that they understand if the humans are having problems with the instructions that are being given? And finally, the bottom picture here for today's talk, we're going to look at an application of using robots in a bartending scenario. What all of these different robot applications have in common is that I use automated planning. And in most of the cases, we use an instance of automated planning called epistemic planning. And I'll talk a little bit about automated planning and then epistemic planning, and then talk about how it can be used in the particular application. So, in general, a lot of the work I do is answering the question, how should an artificial agent sense, reason, and act to achieve its goals? So, if we think about what we as humans do, humans perceive and manipulate their environments by sensing. We look around, we try to understand the scene, by reasoning, by thinking about what we should do, and then by acting. So, actually taking an action, executing it in the world. And the big research question then for me is, how should we do this with an artificial agent? And so today, as I've said a couple times, we're going to look at a particular application of using epistemic planning in a robot bartending scenario to try to answer this question. So, as some motivation for this work and for planning in general, if we think about an agent, so this could be a human or it could be an artificial agent like a robot, an agent trying to achieve their goals in the world, they often have to reason about a couple things. So first of all, what actions, what steps need to be taken, especially if you're trying to achieve some sort of goal in the world? And then the order in which you perform certain actions. So what actions need to come first, what actions need to come next, what actions need to come after those. And informally, we just refer to this process as planning. And we as humans are pretty good at it. We do it all the time in various settings. So think about taking a trip when we're all out of lockdown. Um, you have to think about where you want to go. You've got to buy a ticket. You've got to pack your bags. You've got to go to the airport. You've got to board your plane. You've got to go to the particular location. And the order matters. So, of course, you want to pack your bags before you go to the airport. You can't board the plane until you actually get to the airport. You have to make sure you buy your ticket before you board the plane. So the sequence of steps, the order in which they need to be performed. You think about making a meal, same kind of thing. I need to gather ingredients. I need to mix them in a particular order. I need to cook them at a particular time, and then serve anything. An interesting application of this, though, is the idea of interacting with other agents. We can think about this as also a type of planning problem. I think about who I want to interact with. I think about what I want to say to that person. Do I have different goals I'm trying to achieve? How do I get to those goals by choosing the appropriate words to say or the actions to perform during that interaction? So there's lots of instances of this idea of planning. Automated planning research attempts to understand this process computationally, and we do a lot of work on actually building tools to solve this problem. Epistemic planning, then, is a type of automated planning that involves reasoning about agent knowledge and beliefs. And I'll talk in a little bit about what exactly that means. Needless to say, this is actually can be a really hard computational problem, especially if we're working in real world scenarios. So it's interesting from a research point of view. Now, why bartending? So I've said today's application is going to be a bartending robot, and we could have chosen other domain areas to work in, but why bartending? Well, bartending is very interesting for a number of reasons. There's usually lots of agents involved. It's multi-party, multi-person. It's also quite dynamic. People are doing lots of things potentially at the same time. The interactions are really short. So you might, if you're a customer coming into the bar, you need to order something from the bartender. That's a very short interaction. You're not establishing a long-term companion relationship. You're trying to get your drink or ask for information. From the bartender point of view, you have to get it right. You need to understand who needs your attention, what the requests are, try to service those requests as efficiently as possible and as socially appropriate as possible. So bars and cafes and restaurants, different parts of the world, there are different cultural things you can and cannot do. And so understanding all of that as part of the planning process makes it quite interesting. So I'm going to show you a little video here from the movie Cocktail, just to demonstrate bartending, possibly at its worst. I apologize in advance for some of the language.
Form, young Flanagan. This is the Upper East Side, the saloon capital of the world. Big time. Are you ready for the big time, young Mr. Flanagan?
I think I can handle it.
Get
your act together!
Let's get roses, please!
Hey, come on, man! I got 4 people waiting for me. I'm not going back here with 3 drinks!
I know, it's coming.
With a twist, a hot salute on the rocks, Yubies and tonic, and a velvet hammer!
Is that what I ordered?
And a ring, a Molson, and a Cuba Libre!
What was that?
A Molson and a Cuba Libre!
It's a way to order.
Drink order and first, honey!
Woo!
What is this? Dog to hire the handicap?
You gotta sit in the water, go to Coney Island.
You want me to bite the top off this?
Here, this has got a recipe.
Orderina Cuba Libre!
Cuba Libre.
Have a glass of water!
She doesn't know how to make it.
Where's my Jim Beam on the rocks?
It's coming.
I'm not leaving till I get my Cuba Libre. Excuse me, can I have an orgasm?
This is what I ordered.
Order it.
A white wine. You bitch! Why didn't you just tell me it was a rum and coke? Could I have what I ordered? Bloody Mary!
An angel tip.
A white wine.
Hey, squirrel!
A friar tuck.
A sing-a-ling.
A white wine.
A pink squirrel! Angel tip!
Dirty mother! Can I have what I ordered? All right. All right. Now what was it that you ordered? A martini. What's in that?
Okay, so bartending, and imagine doing that with a robot. So if we take a look at bartending from an interaction point of view, we might have a scenario that looks something like this. So we have a couple people, they come into a bar, they approach the bartender, might be a robot in this case, the bartender might greet them, so how can I help you? And then people proceed to order. So someone maybe orders a lemonade. Another person comes in, tries to attract the attention of the robot by gesturing. It waves its arms. And then the robot says to that person, well, just a moment, please. Serves the first person, talks to the second person, asks them what they'll have. Person orders, serves the person, and then says, thanks for waiting. How can I help? Third person orders, and that person gets served. So even in this simple example, you can see there's a lot going on. We've got multiple people. We have multiple requests coming in. The robot is trying to manage the situation by introducing a type of fairness here, a first come, first serve type of scenario, and then ultimately trying to understand what they want and serving their requests. Now, the interactions here are very much task-based. So the customers are coming in because they want to achieve something, and the robot is trying to understand and respond and ultimately try to achieve what it is they want. And so this makes it perfect for planning as a way of trying to figure out what are the steps we need to take in what order to achieve the goals. So we're always asking ourselves in these kinds of scenarios, what should the robot do next? What is the next action given the current setting? So possibly if it's this busy bar setting, it's actually interacting with one of the customers to serve them a drink. So maybe we have a plan that looks like this. We greet the customer, we ask them for a drink, we acknowledge their order, pick up the correct bottle, give it to the customer, end the transaction. But maybe we have a different scenario here. Maybe what we're trying to do is clear off all the empty bottles that are already on the bar. So we might have a slightly different type of plan. So move to the first location, pick up the empty bottle, put it into the bin, move to another part of the bar, pick up another bottle, put it in the bin. But again, in both cases, we're still answering the same fundamental question. So what should the robot do next in the particular scenario, given the goal that it has? So I'm not sure how many of you have done automated planning before. You may have seen it in a previous course, maybe talked a little bit about strips or PDDL. So I'm going to quickly remind you on what automated planning is. We can think of automated planning as a type of pipeline. So we have the real world, and then we have some abstraction of the real world environment, which we call the planning domain. And we have a particular problem that we want to achieve, the planning problem. We take this description of the scenario, the domain and problem, and we hand it off to the planner itself. So a particular software tool which as output produces the plan. And again, the plan might be similar to what we've seen on the previous slides here in terms of what the robot should do in certain scenarios. So automated planning techniques, though, are good at building so-called goal-directed plans of action, given a suitable domain description. So the planning problem typically consists of some sort of representation of the properties or the objects, the things that make up the world, or the agent's knowledge. We could also include that in our representation if we wanted. Usually described in some sort of logic or logic-like language. We then have a set of state transforming actions. So these are actions that are able to have some sort of effect in the world, to change the world. We have a description of the initial world. So what does the world look like at the beginning of the scenario? Or what does the agent's knowledge look like at the beginning of the scenario? And then a set of goal conditions. So what are we actually trying to achieve? And then a plan is simply a sequence of actions that if we apply that to the initial state is going to transform the state in such a way to bring about the goal conditions. So we're choosing actions with the planner to move us from whatever the start state is to a state where the goal is achieved. Now, there's a couple interesting ideas here with planning that are worth mentioning. The first one is the idea that the representation of the planning problem, so what goes on in this box here, is usually separated from the actual back-end planning engine that actually solves the problem. So in other words, we have a way of representing probably a large set of domains and problems, and the planner simply accepts that as input and produces the plan as output. And this idea is referred to as domain-independent planning. So the planning engine supports a representation language that can model a large set of problems, not just a single domain or a single problem. So we're not building a planner to solve one problem. We're building a planner to solve a variety of problems as supported by the representation language. So if you've done some work on planning in the past, you possibly have come across strips. It's a very old representation. But it's still the core of a lot of planning work that's done these days, because it forms the basis of a language called PDDL, which many modern planners use. But the idea behind strips is that you have some database or some knowledge base that's able to represent information, and we say it's closed world. So it can represent certain information, and we can make conclusions about whether facts are true or false. Actions are the means of change in the world. We have a way of representing actions, and in particular, actions are represented by two properties. They're preconditions, which specify the conditions under which an action can be applied, and the action's effects. And these are the changes that the action makes to the world. And strips gives us an easy way of modeling these kinds of actions. So preconditions can be simply evaluated against the database, the knowledge base, perhaps just by looking up the facts. And effects can be made to the knowledge base by something called an add list, which adds the conditions of the world that are becoming true by applying that action, and a delete list, which removes properties from the knowledge base that the action has made false. The preconditions solve a problem called the qualification problem. And this add and delete list setup helps solve a problem called the frame problem. So we specify the changes that the action makes to the state, and we assume that all other properties are unchanged. And this gives us a simple way of managing state update. So you may have seen examples of PDDL if you've done an introductory course on AI. And PDDL provides a type of common syntax, a type of programming language, if you will, for specifying planning domains and planning problems. So here's an example of what PDDL looks like, or partially, for a classic domain called blocks world. And you'll see it's structured in a certain way that allows us to define the domain, define the properties in the domain, define the actions in the domain with their preconditions and effects. Actions are parameterized, so they can take arguments. And then we can define, and we might have a series of actions. And then we have a planning problem that we want to achieve. So in this case, a description of what the initial world looks like. So it possibly looks like this configuration of blocks here. And then a goal situation that we want to achieve, which might look like a situation here. And then if we were to hand that to a planner, the planner would produce the plan. In other words, the concrete list of actions that would allow us to move from the initial state into the goal state. Now, I don't have much time to talk about how planners actually generate these plans, but you can think of this as simply a type of search through the state-based transition system that we've defined. So the actions tell us how the state changes. We know the state we begin with. So it just becomes a search problem at this point. How do we choose appropriate instances of the action to take us from the initial state to the goal state? So in this example here, for instance, the plan might involve, first of all, picking up this block C from this block A, putting it down on the table, picking up another block, this block E, putting it down on the table, and so on until we build this configuration here. Now, if we think about what's going on with strip style planning, which we also sometimes refer to as classical planning, we have the knowledge state of the agent. So what the agent is thinking about in terms of its model of the world, and it pretty well matches exactly what the world state is. Strips in particular make some simplifying assumptions in terms of the information being correct, the information being complete, the actions being the only way that the world can change. So we can think of the agent's knowledge in this case being almost a perfect mapping of what the world state looks like. Epistemic planning, on the other hand, tries to deal with the agent's actual knowledge or beliefs about the world and other agents. And this information might differ from the true state in certain ways. So if you think about a robot that's operating in its local environment, so maybe it's the Pepper robot that's rolling around the department at Sapienza, it doesn't necessarily know anything about any other part of the world outside of the building that it's already explored. So its information is very localized. It might have certain knowledge or certain beliefs about what happens outside of that environment, but maybe not. It may be restricted. An agent might be able to sense the world, to gather information, and it could possibly reason about those outcomes. But it might not necessarily know what those outcomes will truly be until it actually executes that action. So again, this is an epistemic idea here. It might have beliefs about how the sensing could turn out, but it won't know for sure until it actually executes the action. An agent might be interacting with another person, and it might be able to guess what that person will say in response to say, a question you ask. But again, it won't know for sure. It just has certain beliefs. And then the agent might even have beliefs about what another agent believes about it. So there could be a nested idea here of believing something or adopting the beliefs of another agent. And those beliefs aren't necessarily true in the world. So we're moving away from this kind of classical planning model here to something a bit more complicated. So we may have a situation that looks like this now, where in the real world, we have a particular configuration of blocks, for instance. So E is on D, D is on B, C is on A. There's two towers that are sitting on the table. But the agent might believe that the blocks are actually configured this way, that the D is on B, B and A are on the table, and in fact, it's holding E. So that's perfectly fine. That's a perfectly acceptable belief state. It just doesn't happen to completely match reality. And epistemic planning gives us the power to represent these scenarios. There are also types of epistemic planning, as I said, where we can reason about the beliefs of other agents. And this is very, very powerful and potentially really useful in all kinds of planning scenarios. So here in the real world, again, we might have a certain configuration of blocks. Then there might be another agent that has a certain belief, again, about how those blocks are configured. In this case, this agent's beliefs are in fact incorrect. And then our agent here might have beliefs about that agent's beliefs, about what it thinks how the blocks are configured. And our agent's beliefs about that agent's beliefs might in fact differ from what that agent's beliefs are actually in the real world. And in fact, in this case, our beliefs about that agent's beliefs are also wrong. So again, we can have a lot of interesting, very powerful machinery here in terms of representing ideas of knowledge and belief and how that relates to the real world. So some questions that we may want to ask ourselves if we're thinking about these kinds of models is, well, first of all, how can such information be represented? If you remember the pipeline I showed you before, planning is all about representations of planning domains and planning problems that are then passed to the planner. So if we're using an epistemic planner, what kind of information can be represented? Is this information always complete? Is it always correct? In terms of actions, what are the consequences of actions when we have this kind of model now in the world? Are there other types of actions that can be modeled? So for instance, can I model the effects of sensors now? And then how do we use this information to generate plans? And are there differences between the kind of information that we reason about at a planning time and the kind of information we reason about when we actually execute these things? Okay, so today I'm going to talk about a particular application and a particular epistemic planner called PKS, which stands for Planning with Knowledge and Sensing. And this is a somewhat old approach now that I worked on back in my PhD days. The planner is still being developed. We still use it for a lot of our robotic applications. There are other epistemic planners that exist. I'm not going to mention those today. But I'm going to give you a little bit of the flavor of how PKS works and then how we apply it in the bartending domain. So first of all, PKS is able to work with incomplete information and sensing actions. So we're able to represent information and not assume that the agent has complete information about the world. We're also able to model the effects of actions that are able to gather information about the state of the world. Now, PKS is based on an extension of the strips idea. So if you remember when I talked about strips, we had a single knowledge base which represented all the facts, all the information about the world. In PKS now, we have a set of knowledge bases. We have 5 knowledge bases, each of which model a different type of information. So this gives us a richer knowledge representation to allow us to reason about different types of knowledge and how our beliefs and how these interact with each other. Actions now are modeled as changing the planner's knowledge state rather than, sorry, there's a typo here, rather than the world state. So we're no longer reasoning about how the planner, say, directly changes the world, but how the planner's knowledge is going to change as a result of executing actions that will change the world. And all this information about knowledge and action can be formally understood in terms of a modal logic of knowledge if we were interested in actually analyzing the types of domains that we have. So a key idea here in this representation is the idea of a world level action versus a knowledge level action. So the pickup action here on the left-hand side is an example of, say, a standard PDDL action. I can pick up some block X if my hand is empty and X is on the table, and as a result of picking up X, it's no longer the case that my hand is empty, it's no longer the case that X is on the table, and I, or the robot, is holding X. So the action makes reference to properties of the world and how the action changes those properties of the world. In the knowledge level version now, we raise the problem up to the level of knowledge and beliefs. So we can talk about picking up some object X, but now as a precondition, we want to say, I need to know that my hand is empty. I need to know that the block we're interested in is on the table. And as a result of applying this action, the agent now comes to know the fact that its hand isn't empty. It comes to know the fact that the block is no longer on the table, and it comes to know the fact that it is holding that block. So in other words, there's a lot of similarities between these two actions, but we've raised the problem up from the level of just reasoning about the world to reasoning about the beliefs of the agent that we're trying to model. So the way we do this in PKS is through its representation language, which is modeled in terms of the 5 different knowledge bases that it can use. So the first one is a knowledge base called KF, which represents knowledge of facts about the world, positive and negative facts. So this is very similar to the standard strips knowledge base. The main difference here is it's not closed world. So in other words, there can be information that we just don't know anything about. Facts of the world, we have no idea if they're true or false. They're simply unknown to us. And we can represent instances of particular information. The KW database allows us to represent the agent's knowledge of binary sensing effects. So these are actions, a particular type of information gathering action that could return one of 2 possible values. So is something true or false? Is the answer yes or no? Is an object on or off? So it's a type of sensor that we're modeling at the planning level that has, again, it has 2 possible states. And we don't know what those states will necessarily be until we execute the action. But we can represent that type of information at the planning level. The KV database is really an extension of KW that enables us to represent sensors that are multi-valued. So imagine something like a thermometer that's able to tell us what the temperature is. It might return a range of possible values, and we could use something like that together with KV. The KX database allows us to represent a particular type of disjunctive knowledge called exclusive OR knowledge. And so this is the idea that we might know that one of a set of possibilities are true, but we just don't know which. And so we can represent that information here. And then finally, the LCW database allows us to represent local closed world information. And the idea here is that the agent might have complete information about very particular contexts in the world. So it doesn't know everything about everything in the world, but it might know everything about particular aspects of the world. So for instance, if I'm carrying a box, I might know the contents of that box, all of the objects that are in the box. So that's an example of a type of very localized closed world information. I'm going to mostly focus on using the first three databases in the examples I give in the bartending domain. But just keep in mind that the representation is quite a bit richer than that. So that's representation. On the reasoning side, PKS has a very simple, very primitive type of query language that allows us to ask some very basic questions about the knowledge state of the agent. So first of all, we could ask, is some formula known to be true? Do we know the value of some function? And is some formula known to be true or false? We can also talk about the negation of these queries. And these represent really the three basic aspects of knowledge that you see in many of the logical accounts. So do I know something to be true or false? Do I know the value of something? And do I know whether something is true or false? Now, the way that PKS works with this information is it ultimately queries the different databases. But in order to answer these queries, it may have to consult more than one database. So if you have information in the KF database, for instance, and maybe in the KX database, you could combine that information in a way that allows you to come up with a more accurate conclusion. So reasoning does involve querying the databases, but it's more than just single database lookup. So actions then in PKS, and we've already seen one example of this, are formed by, in the same way as P2DL, with preconditions and effects. But the preconditions now are primitive queries using our reasoning language, and effects are updates to the particular databases. So here for the grasp action, we've defined an action that says I can grasp some object if I know my hand is empty and I know the object is on the table. So these two references with the K's here are just primitive queries of the kind that we've seen here. The effects now are saying I'm going to add to the particular database, in this case the KF database, the fact that the hand is not empty. And here I'm going to add again to KF that the object is not on the table, and here I'm going to add to KF that the object is in hand. Now we can do more complicated or more interesting actions in PKS. In particular, we can model different types of sensing actions. So say, for instance, that we want to sense the weight of an object, like this cup. So I can do that if I know that that object is in my hand. And as a result, I come to know the value of the weight of the object. So in other words, I have an effect here which adds to the KV database the weight, a formula that represents the weight of the object. So essentially what we've done here is we've modeled a type of sensing action, an information gathering action that our agent can use. Here's another example, an action that might sense whether or not an object is empty. So I can look in my cup, see if there's any tea in the cup. So I need to know in this case that the object is on the table, and as an effect of that, I'm going to come to know whether the object is empty. So in other words, this is modeled as a primitive query, querying the knowledge state. This is modeled as an effect which updates the KW database, the know whether database, with information about whether or not the object is empty. Epistemic planning then with PKS is now a search through the knowledge state transition system. So in other words, we still have this state-based representation like we saw before, but now it's constructed from all of these databases that we have. And when we apply actions, we're simply modifying the contents of those databases to reflect the new database state that results from applying those actions. And planning then is just simply searching, again, selecting the appropriate actions that are going to give us the types of state transitions we need to achieve the goals. Goals for us now in PKS are going to be a set of the primitive queries. So in other words, they're going to be conditions on the knowledge state of the agents involved. Okay, so that's a little bit of background on planning, epistemic planning, PKS. What does this all have to do with robot bartending? And the work I'm going to tell you about now is from a project that was called JAMES, Joint Action for Multimodal Embodied Social Systems. The URL is there if you're interested in looking up some information about this project. But we've already seen examples of how interesting a domain bartending is. That we have this complicated environment, and we need to understand what to do and to react appropriately. And we've seen some technology, of course, for generating plans. Things are, of course, more complicated in the real world. So if we're using something like a robot system, planning becomes part of the architecture. Planning is integrated within this larger system that needs to take its inputs from the real world and produce the planned outputs that ultimately are going to be executed. So in James, we had an interesting robot. It had a cat's head. It was animatronic. It could speak, it could nod, it could smile, it could blink its eyes, it could tilt its head. It could do quite a bit of emotional expression on its face. We also had 2 large robotic arms which could be used to manipulate various objects. So it could pick up bottles, it could hand them over. On the input side, we had speech recognition and we had visual processing. So the system could look at the scene, try to understand what the social contexts were, so where the agents were, what they were doing, did anybody say anything? And all that information was put together into a type of state that the planner could then use for doing the kind of planning that we just talked about. The output of the planner then was then post-processed in a way that it could control the information going to the cat's head. So is the cat supposed to look at somebody? Is it supposed to nod? Is it supposed to say something? And what the robot arms were meant to do. So is it going to pick up a bottle and actually hand it over to someone? So that's the architecture. And again, this can end up being quite complicated. You have to do all this information, all this processing to put the information you need in a form that the planner can use it. And then the plans need to go somewhere, and some part of the system needs to interpret those plans to actually execute them in the world. So if we look back at the interaction that we had in the bartending domain, we can consider some of the parts where the robot is meant to act and see that really these are instances of different types of actions. So if the robot says, "How can I help you?" it asks a question. This is really a type of information gathering, or really a type of sensing action. And we've already seen that we can model different types of sensing actions with PKS. The robot serving someone, so actually, for instance, picking up a bottle and handing it over to a customer. Well, this is maybe similar to a type of physical action. This is like block swirl. This is picking up an object and putting it somewhere else. In these kinds of domains, we also have these other actions, though. So the robot will do things like say just a moment, please, or thanks for waiting. And we can think of these as social actions. These are actions that are there to facilitate the interaction. We do this in conversation all the time. So the robot should do something similar. And the question is, what does this mean in terms of our planning domain? How do we represent all of these different types of actions, and what effect does this have on our models? So first of all, in the bartending domain, we can think of the types of actions that we might want to perform. And so here I've generated a list of actions, and you'll see that they're all at a pretty high level, first of all. So we can talk about concepts like greeting an agent, asking an agent for a drink, serving an agent a particular drink, saying goodbye to an agent, maybe telling an agent to wait, or please wait a moment, I'll get to you in a second. Acknowledging them, thanking them for waiting, acknowledging that we got their order. Okay, you ordered this drink. We might be able to answer certain questions if someone comes in and say, what types of beer do you have? Then we want to inform them. So how you go about modeling domain really depends on what you want your agent to do, of course. In this case, we were interested in what human bartenders actually did. And so some of our partners from Bielefeld, Germany, they were working on the James project with us. They sent some of their master's students into real bars, and they collected, I think, hundreds of hours of video footage of bartenders, human bartenders, interacting with customers. And then we tried to look at those and understand what were the kinds of actions that the humans took, and tried to map those onto the planning domain. So our choice of action here was really dictated by the types of actions that humans tended to perform. In terms of domain properties that we use in our planning model, again, these are very high-level properties. So things like, is an agent seeking the attention of the bartender? Is an agent visible? Is an agent part of some group? So have a group of people walked into the bar. Who is the agent transacting with? What drink has the agent requested? And so on. And again, all of this information was really inspired by the types of information that was collected from this real data collection in bars in Germany. So given this information, given the domain properties, given the types of actions, we then tried to model these actions in PKS. And so here's an example of 4 of the actions that we had in our domain. So I'll just look at a couple of these. So greet, for instance, we could greet some agent, provided we knew we weren't transacting with someone, we knew that person hadn't ordered, and as a result, we'd come to a state where we knew we were transacting with someone. So again, you can see the knowledge representation being referenced here, the primitive queries in terms of the agent's knowledge state and the effects. A more interesting action is this one here, asking for a drink. We can ask an agent for what drink they want, provided we know that we're transacting with that agent, we know that agent hasn't ordered, and then as a result of asking for the drink, we're going to come to know that they've ordered, and we're going to come to know the value of the drink they requested. And this is the really interesting part from the epistemic planning point of view. We don't know until we actually execute the ask drink action what that agent is going to say. They might order a wine, they might order a beer, they might order a lemonade. We don't know that. However, we can model the fact that this is a type of sensing, a type of information gathering, and that we will have knowledge of the value of the drink they've requested. And it's a really powerful concept, and allows us to do some interesting things in terms of planning, as we'll see in a second. And then serving a drink, This is an example of a physical action. So we can serve a drink to an agent provided we know we're transacting with them, we know they've ordered, we know the value of the drink they've requested, and we know that that drink is in fact drink D. And as an effect, then we'll know we've served them. So, and then goodbye is kind of an analog to greet. Provided we're transacting, we know we've served them, then we can end the transaction. So we have quite a number of different actions here. We've got instances of social actions, we've got instances of sensing actions, we've got instances of physical actions. So now we can simply hand this to the planner, and we can ask it to generate a plan for us. So in this case, here's an example of probably the simplest plan we can generate for a single customer that comes into the bar that's seeking attention. And it's just a simple 5-step plan. So we can greet the first agent, we can ask them for their drink, acknowledge what they've ordered, and then we can serve that agent the drink they've requested, whatever that is. So at this point, until the plan is executed, as I said before, we won't know what actual drink they ordered, but we can still generate a plan to serve them whatever drink they requested. And that's, again, a very powerful type of reasoning we can do at the planning level here. And then we simply end the transaction. So this is the simplest possible plan. It's a single customer coming into the bar. The plans are built in response to customers seeking attention. So we don't pre-build this plan. We build it on the spot when the system recognizes that there is somebody in the bar that's trying to get the attention of the robot bartender. And it really represents a type of best case scenario based on the beliefs we have. Now, of course, we can do things more complicated. So say 2 customers come into the bar individually. So we can generate a plan that looks similar to the scenario we had earlier. So first of all, we could tell one of the customers to please wait a moment, greet the other customer, ask them for a drink, acknowledge the drink, serve them the drink they requested, thank them, say goodbye, and then thank the other customer for waiting, and now proceed with the transaction to get their order, serve their order, and thank them. Again, the important thing here is that this is generated in response to the scenario of 2 customers coming and asking for a particular drink. It's not pre-generated, even though it looks like we're kind of generating the single agent plan and putting it together. The planner is actually reasoning about which actions need to be performed in which order. We also looked at instances of when customers come in groups. So in Germany, the tradition is that if a group of people come up to the bar, the bartender will ask each person in the group in order for their drink, serve their drinks, and then move on. So in this case, we have a single greet. We greet one of the people. In general, we just greet the group, but we greet someone on behalf of the group. We ask the first person for their drink. We acknowledge it. We then ask the next person in the group for their drink, acknowledge it, serve the first person the drink they requested, serve the second person the drink they requested, and end the transaction. Again, if we had a different type of protocol, so in the UK, for instance, it's typically the case that one person acts as a spokesperson on behalf of the group. So you would talk to your friends, get their order, and then you tell the bartender. We could also model that with a planning solution if we wanted. We could also do more complicated type of plan generation if we wanted to reason about the different types of drinks, and for instance, say follow up with additional questions. We can form a type of plan that has branches in it, a type of contingent plan. I haven't really spoken about contingent planning. I don't really have a lot of time to do that. But I just want to acknowledge the fact that for instance, we could have a plan that, for instance, greets, asks for a drink, and then reasons about the types of drink that we could have that the person could have requested, and then in each case possibly gone into a type of sub-interaction. So if they ordered juice, we might ask if they want ice in their glass. If they ordered water, we could ask if they want it in a bottle. If they ordered beer, we could ask what type of beer. So again, it allows us to look at the information being gathered and then reason about the possible outcomes and form branches in the plan to consider ways that the plan can evolve. And again, this is another powerful technique that we get from using this type of epistemic approach, reasoning about the outcomes of knowledge. And then finally, we could keep scaling these domains up. So here's an example of a plan for 3 customers that come in to interact with the bartender. As you see from the picture here, there wasn't much room at the bar to fit more than 3 people, but from the planning domain, we could kind of scale this up arbitrarily. So now I'll show you a couple videos of the bartender in action. So the first one here is simply the example of the single agent plan. So the planner generating a plan for one customer coming to the bar to seek attention.
Hi,
Hi,
what do you want?
give me a water, please.
Here is your drink.
Thank you.
Bye.
Bye.
So you'll see there in that interaction that the robot basically followed the plan that we showed earlier in the talk. So it greeted the customer, it asked them for their drink, it acknowledged the drink, it picked up the drink, it handed over, it thanked the customer. This was an early version of the system, so the robot's a little bit slower than it ended up being towards the end. Also, these are really large industrial arms. They can actually do some damage to you. I think they can lift 100-kilo loads. So it was also slowed down on purpose just to make sure nobody got injured while ordering a drink. Okay, here's another example of 2 customers coming in, but in this case, one of the customers isn't going to order anything. So it's not seeking the attention of the bartender, and the planner and the system does the appropriate thing.
Hi,
Hi,
what would you like?
give me a water, please.
Here is your drink.
Thanks.
Bye. You're welcome.
Bye.
So in this case, again, we saw the execution of the single agent plan, and the second person in the scene there wasn't trying to get the attention of the bartender, and so the planner didn't need to consider a plan to interact with that person. In this case, we've got 2 customers coming into the bar, and now both of them will order drinks.
Hello,
Hi,
I'll be with you in a minute. What do you want?
I would like a water, please.
There you go.
Thank you.
Goodbye. You're welcome. Thanks for waiting. What do you want?
Give me a Coke, please.
Here is your drink.
Thank you.
Goodbye. You're welcome.
Bye. Bye.
So in this case, we saw the full two customer plan where one of the customers was told to please wait. The interaction went through with the first customer. The second customer was thanked for waiting, and then went through the interaction for them to order the drink. So I just want to quickly point out we could also do purely physical tasks in the domain. So if we simply consider the other scenario that I showed you a picture of way back at the beginning of the talk of clearing, for instance, the empty bottles, we could use the same type of technology, the same type of planning model, and in this case, not worry about interaction, simply worry about the physical actions of picking up appropriate bottles and removing them to other locations, for instance, to put them into a bin or ultimately move them into the dishwasher. So in this case, exactly the same planner, some extra actions to reason about whether or not bottles were empty. And then in the project, I just want to point this out, we also consider different embodiments. So the robot shown here has a very different type of embodiment. It doesn't have the cat's head anymore. It's kind of a one-armed bandit robot.
Als Teilzeitkraft. Der Barkeeper aus Metall heißt James und soll einmal die perfekte Tresenbedienung werden.
But you get a sense of what the robot
Was wollen Sie bestellen?
Was hast du denn?
And again, the idea here is we can change the embodiment, but the type of reasoning we use, the type of planning model is pretty well unchanged. It allows us to do this very abstract, high-level type of reasoning about beliefs, allows us to generate similar plans, even though if ultimately the physical embodiment looks, in this case, quite a bit different. Okay, the last concept I just wanted to mention, I know I'm running a little long, is when we go to execute these actions in the world, it isn't usually the case, especially when we're dealing with people, that the plans work out as we had originally planned. So when we execute actions in the world, we're always monitoring how our plans are going and whether or not there's any changes between the states we expected to be in and the states that we're actually in. So one example of this is when we have low confidence speech recognition. So in other words, the system doesn't understand what someone has said. So we planned an action to ask an agent for their drink order, and then the person says something, mumble, mumble, mumble. The system doesn't recognize it, so they weren't understood. So in this case, by monitoring the difference between the expected state, where the plan told us we would be at, and the actual state of the world, we could simply just generate a new plan. We could say, okay, we're somewhere where we didn't expect in terms of the state. Let's just give me a new plan. So in this case, we could generate a plan automatically to say to the person, I didn't understand what you said, and then proceed with the plan as before. So ask them again for their drink order and continue. Another interesting example of where execution monitoring and this replanning idea comes in is sometimes humans will provide more information than you expected. This is an idea called over-answering. So you greet the agent, And then before you get to the point where you ask them for the drink, the agent says to you, "I'd like a beer." At this point, it makes no sense to use the ask drink action because the person has already supplied the information, that the effects of that action are already achieved. So in this case, replanning would allow us to simply go to the state where we serve their drink and then continue with the transaction. So the important takeaway message here, though, is that monitoring is really important in real-world domains. That plans, when it comes to execution, don't always end up the way that you had originally expected, and you may have to rebuild your plan. Okay, if you're interested in how this project actually went, I'd refer you to the website. We did run lots of experiments, bringing real people in to order drinks and things, and we had a pretty good success rate on actually delivering those drinks. The interesting thing from a planning point of view is that the planning is really quite short. So in all of these instances, we were generating plans in a fraction of a second. And even when we had, say, 3 customers, this only required plans that were 17 steps long. In a system like this, basically, if you're interacting, responding to a human within a couple seconds, it's usually okay. As you saw from the video, the robot motions were also really, really slow relative to the reasoning time. And so you could imagine parallelizing the planning with other activities. The one interesting observation we had from this is that replanning was really, really frequent. It was rare for us to get through a plan without having to replan some step. So being able to generate plans very, very quickly was actually quite a benefit for us in this scenario. Okay. So just before I wrap up, I just want to mention that there are, of course, other applications of these kinds of techniques. So instead of actually, for instance, taking orders like we saw in the bartending domain, you could imagine a type of instruction giving domain instead, using very similar types of information and similar types of plans. So, asking people where they want to go and then giving them directions to get there. A nice application. In fact, we've got a project on the go that's looking at using epistemic planning for this kind of task. Another example of where these techniques could be used have to do with explainability and the idea of explainable AI or explainable planning. As you've seen from these examples, the models we're using here are very rich. There's lots of information about how the agent makes decisions and what that means in reference to its knowledge state. So we could imagine adapting the system to answer other types of questions. So why was a particular action chosen? Well, it was chosen because the agent had particular beliefs about the world. What would happen if we chose other actions? What's the system trying to achieve? So I think these kinds of techniques work really, really well with the fact that we have these rich models, and so we can talk about explaining things in terms of the beliefs of the agent. Okay, so there's one question. So the question is, the fact that we refer to a belief state, so to an uncertain information about the world, does not represent a problem on the robot's behavior predictability. If yes, how can we overcome it? So so there is, I guess there's 2 things at play here. So first of all, I am representing information which is potentially uncertain. In this type of planning, I haven't talked about numerical uncertainty, but it could be the case that we have probabilities attached to everything. And so all of the information I'm reasoning about is in fact uncertain. Worse yet, when you're using it on a system like this, the information that the planner is getting is only as good as the sensors that are gathering that information. So if you remember the domain model, the architecture diagram I showed earlier in the talk, The state that the planner uses is based on the visual state and the audio that's being recorded on the speech recognition side, and those are combined into a type of state representation. So if there's noise or uncertainty in the sensors, then there's going to be uncertainty in the model, in the state representation that the planner uses to make its decisions. Even if the planner decides on the appropriate action, it is then possible that actually executing that action in the world isn't going to necessarily have the effects. So the best you can do in some cases is to really just continually do this type of sensing and reasoning loop to see, is the information coming in correct? Am I making the correct decisions? Are they being executed correctly? And to try to recover as best as possible. And over time, hopefully, the system is making the long-term correct choices. But you may get it wrong, and you may just have to replan. So the type of models we have here at the planning level, we can account for some of the uncertainty, for instance, in terms of the belief state. So we could model the fact that, sometimes it's the fact that the sensor fails. And I could build a type of plan, a contingent plan, for instance, that accounts for that failure potentially at planning time. So that's a great question. Yeah, there's a lot going on here in terms of uncertain information. Some of it due to the sensors, some of it due to the effectors, some of it we can overcome through replanning, some of it we can overcome just within the planning model itself. I hope that answers your question. Okay, so let me just conclude. Oh, let me just say one final thing. One thing I didn't talk about here was this idea of using nested knowledge. And of course, we could have scenarios where we are actually reasoning about the beliefs of other agents and possibly about their beliefs. And you can probably dream up scenarios where you're asking other agents for information, and you realize they have a particular belief, and then maybe your agent needs to decide, do we adopt those beliefs? Or how do we trust those agents' beliefs? How much should we trust those agents' beliefs? So using this idea of nested knowledge is also really, really powerful for epistemic planning, and we really haven't gone into that today. So just to conclude then, I hopefully have convinced you that epistemic planning can be applied to a variety of problems involving both task-based interactions, but also human-robot interaction. It gives us the ability to model very, very rich domains. Also, just using planning in any form gives you the ability to model domains where you can very easily change the initial state, you can change the actions, you can change the goals, and you don't have to change the planner. So if the situation changes in the robot's operating environment, you have a way of reacting to that. You have a way of still generating plans. And I've given you some hints on other types of applications like explainable planning, ways you could connect task planning to motion planning. You can also apply these things in multi-agent scenarios. There's also a lot of work being done on actually learning these planning models. So if you're interested in any of my work, in anything I've said here today, I'll refer you to my website. The URL is there. My email address is on the title slide. Please feel free to email me. I'll wait a few more seconds if there are any more questions in the comments, but otherwise, thank you for listening, and cheers. Okay, I don't see any other questions coming, so at this point, we're going to take a very short pause, maybe a couple minutes, and I'm going to hand off to Mary Ellen, who is going to lecture for the next hour. Okay? So thank you very much, everyone.
Ron, Luca just asked, is the PKS system available for student projects? Yeah. So Ron says, yes, the PKS system is available for student projects. You should email him. And I think we're going to send these slides to Luca afterwards. So he'll make these slides available so you can look at all the stuff again. Yeah. Right. So that was Ron. And now he went a little long. So I'm going to go a little bit, hopefully short, so that you'll still be finished in sort of the 2-hour time. So this is me. My name is Mary Ellen Foster, and I am a senior lecturer in computing science at the University of Glasgow. And so Ron and I work together on some especially on that James project that he mentioned, but we collaborate on a bunch of things. But I'm more of a social roboticist, and really he works on the AI planning side of things, and I tend to work more on the social interaction side of things. And Ron, can you closer? And so this is me. I'm a computer scientist. I've been in Glasgow since 2015, and so Ron probably said he did the visiting professor thing at Sapienza 1 year ago. The year before that, I actually did a visiting professor at Sapienza and taught on the same HRI course then. And he probably said we were really looking forward to coming back to Rome this year, which obviously isn't happening in physical mode, but at least we get to talk to you guys virtually for a little while. And my background is actually in computational linguistics, so especially natural language generation, and more recently applying sort of linguistic interaction to social robots. And if you want to sort of summarize what my research is, what my research goals are, what I work on is trying to look at how do humans talk to each other face to face, which obviously involves not just transmitting logical forms or even just transmitting words to each other, but there's a whole lot of stuff to do with body language and facial and gaze and facial expressions and gestures and all these sort of prosody, all these things that happen when we have a face-to-face conversation with each other, and trying to sort of implement that on a robot so that you can use the same mechanisms that you use to talk to people to also talk to a robot. And why should we want to do this? I'm not actually going to show this video because I'm a bit short on time, but I encourage you to go to YouTube after this is done and look at it yourself. This is just showing that even very small children really treat robots as social entities, that they really want to, humans really are social. And another fun thing to look at is this Twitter account of Faces and Things. People really do see, we're just essentially wired to try to treat anything as kind of a social partner. And it's useful in the robotic side to not try to ignore that, but to try to actually use that to make robots easier to interact with, more fluent, smooth interactions by taking advantage of the fact that people want to have social conversations with other people and try to let people have some sort of similar social conversation with a robot. So that's kind of my overall research goal. That's kind of my dream. Obviously, we're quite far from actually achieving that. But what I am going to talk about is a few projects that I've worked on where we sort of try to get towards some aspects of that face-to-face conversation. And one of them is, and the first project I'm actually going to talk about, I'll skip this as well, but this is, obviously social robotics is also something that we have top-down ideas from and how they should work in popular culture. But I'm not going to talk about sort of social robots in that sense. I'm going to talk about social robots we've actually built. And the first system I'm actually going to talk about is the system that Ron just finished talking to you about. So obviously I don't need to introduce it. But Ron talked about sort of the action selection side of that system. I'm going to talk about something that he mentioned kind of in one sentence, which is taking all the low-level signals and turning them into a state that the planner can reason about. And that's not sort of a trivial task, actually, and that's one of the main things that I worked on the James system. So as he showed you, bartending is really about managing a social situation. There's two aspects of that in terms of figuring out what's going on. One of which is, here's a bunch of people in front of me, which of them actually wants me to pay attention to them? And then once you figured out who actually wants attention, what is it that they actually want? And both of those are actually difficult things to do in this kind of talking to real humans who do weird things type setting. And so I'll focus on the who needs attention side first. And as Ron also said, we had some partners in Germany who went into bars and checked what do people actually do when they want the bartender to notice them. And it turns out that what people do, and not only did we use that to decide what actions the robot should do, but also what actions should we detect in the people. And turns out what people do if they want a robot to notice them is they stand close to the bar and they sort of direct their gaze towards the bartender. And they sort of stand there for a little while, and if they still haven't been noticed, maybe they sort of reshift and get back into that position. But in something like more than 95% of the interactions we recorded, pretty much those two signals, standing close to the bar and looking at the bartender, were the main things that people did. But of course, we're computer scientists. You can't just sort of take these simple, you can't just sort of take simple rules and implement them like that. We decided we wanted to actually try to use some sort of more data-driven machine learning type approach to do this. So we implemented various ways of trying to figure out of customers in this robot bartender setting who is actually trying to get the attention of the bartender and who isn't. So we experimented with, on the one hand, we tried using that rule. We knew that people, if they stand close to the bar and look at the bartender, we defined a threshold for what does standing close to the bar mean, what does looking at the bartender mean in terms of head angle, and we had that as a rule. Then we also tried separately supervised learning. So we had data from the first user study that we did of people who were trying to get the attention of the robot, people who weren't, and so that's labeled, so we could do sort of supervised learning on the vision data to try to classify, is this person trying to get the attention of the bartender, yes or no? And we experimented with this in several different ways. We did an online user study, like we ran one or the other of these rules live while we were doing a user study to see which did a better job of picking up the people who wanted to get the attention of the bartender. We had this labeled corpus, so we were able to do cross-validation on that in the standard sort of information retrieval metric sort of way, precision and recall and so on, how did it do? And then we also recorded a separate small test corpus so that we could run sort of like cross-validation, but train on our original training corpus, but test on a newly recorded test corpus, which is kind of the halfway between the cross-validation and the full user evaluation side of things, to try to see how did all these different techniques perform in terms of actually classifying people. Does this person want the attention of the bartender, yes or no? And the results of all of this that I'm talking about are presented in the journal article I link at the bottom of this slide. So if you look at the classifier performance, how well does each type of classifier perform on the data? In terms of cross-validation, what did really, really well was an instance-based classifier. That's what the IB1 thing is there on the left. That did amazingly well on cross-validation on its own training data, and really, really bad if we gave it any data that wasn't part of the training data. So clearly that one's kind of overfitting. Other ones, so JRIP, for example, is a rule inference engine. There's ones to do with SVM, there's to do with logistic regression, naive Bayes. 0R is kind of a baseline classifier that always chooses the most frequent case. So you can see a lot of the ones that did really, really well in cross-validation did not so great when given any data that wasn't part of their training, any slightly different data, different lighting conditions, whatever. But the big thing that we actually took away from this experiment was not so much, we sort of threw a bunch of different supervised classifiers at it. It did kind of okay. We took that rule that the sociolinguists told us about, it actually did better than we spent all this time labeling data and training classifiers, and turns out that what actually does better is just if the sociolinguists, if the psycholinguists tell you, social psychologists say, here's how humans behave, maybe you should believe them instead of trying to reinvent social psychology through supervised learning. So this is one lesson we took away from this. The other lesson is don't use a frame by frame classifier. You should use some more temporal classifier. So we did try after the fact doing a different classifier using conditional random fields, which instead of classifying each frame of the video one at a time to say, do they want attention in this frame, in this frame, in this frame, to actually use something that captured a bit more of the temporal structure. And that actually as well did better than most of the frame by frame classifiers. And especially if you look at how does it classify, what this is at the top is the gold standard labels for one training instance, which is, they don't, the yellow is they don't want attention, and then the blue bit they are seeking attention. And you can see in the training data, it changes very infrequently. With these frame by frame classifiers, they're kind of flipping back and forth all the time in terms of, do they think they're seeking attention? Yes, they are in this frame. No, they aren't in the next frame. Whereas again, the conditional random field, not only does it do a better job of getting the classification right, but it also does a better job of staying stable. So here the rule is not good at that. What the rule is good at is kind of more generally across the whole corpus at identifying things better. But the main takeaway from this study for me is actually is that, as I said, if you're trying to use the mechanisms of human interaction to implement an interactive robot, and people who understand human interaction tell you something, you should believe them instead of possibly trying to reinvent that using data-driven methods. Sometimes data-driven methods can help, but if there's a really, really clear 95% of the time, here's what happened, maybe you should just believe them. So that's one lesson I actually took away from this project that I'm trying to use a bit more in my subsequent work. And just a tiny, tiny bit about not only, if you figured out who in front of you needs the attention, you also need to figure out, this person wants something from me. What is it that they want? In the case of the bartender, what drink do they want? And if you look at all the system evaluations we did through most of the project, they all we looked at various things. But one thing, if you look back at all of the recordings and what happened in all of those, is that the system would tend to, if it heard a random noise, and if the speech recognizer thought it might have been a drink order, it would sort of go, right, okay, here you go. So with the speech recognizer we were using, it would be kind of, someone would make a random noise and the system would say, right, here's your Coke, and hand over a Coke, which obviously that's not the behavior you want. So right at the very end of the project, we realized we actually had a state representation that was not rich enough. So the state representation we were using right up until the end was the dark blue in this slide, was just, here's a property, here's a value. And this is the representation that all the stuff Ron talked about used as well. There's a property, it's got a value. We realized that was throwing away a lot of interesting stuff in the state, including, especially from the speech recognizer and also from the vision system, we would get not just the data, but the data and an estimate of how confident that particular sensor was in the data. We were throwing that out. We were basically thresholding it, but throwing out anything below a certain confidence. And also, especially from the speech recognizer, we wouldn't get one hypothesis, we would sometimes get several, but we would only look at the top hypothesis. So what we did right at the end of the project was we added the light blue bit to this slide. So every property has a value and an estimated confidence in that property. And then that also means that for some properties we could include multiple hypotheses. So maybe we think they ordered a green lemonade, but maybe we think they ordered a blue lemonade. And we can keep both of those in the state. And we tried to change the interaction manager a bit to deal with this new state representation. And we did do one final experiment. But the summary of that experiment is we didn't do as good a job as we could have of dealing with this uncertainty, in the sense that what would happen in practice, someone would say, I'd like a green lemonade. And then the system would try to confirm that repeatedly to get the confidence up. So it would go, I'd like a green lemonade. Did you say green lemonade? Yes. Did you say green lemonade? Yes. Did you say green lemonade? Yes. okay, here's your green lemonade. Which means that in the final results of that study, we had fewer wrong drinks were served to people, but people really hated it. Is a problem. And then the thing is, the project finished, so we weren't able to update the interaction policy. But again, another lesson learned for me from this is include all this information in the state from the very beginning, and make sure you can reason about it properly and test your procedures for reasoning about it, so that you don't end up in situations like we did in this study at the end. So that's all I'm going to say about James, because I want to talk about a couple other projects I've been working on. I won't show you that video just now. Including this is a project that has just finished, which I was coordinating. It was a 4-year European project called Mummer, where our goal was to take this robot, Pepper robot, that I'm sure all of you know, and to deploy it in a public shopping mall, and to develop the software to let it have engaging and interesting conversations and socially intelligent conversations with members of the public in a shopping mall. And this was obviously a huge undertaking, because we wanted to run not just kind of the built-in stuff that generally runs on Pepper, but sort of state-of-the-art vision, state-of-the-art social signal processing, state-of-the-art interaction management, state-of-the-art navigation and localization, and have all that work robustly and autonomously in a public shopping mall for 14 weeks, which we did. Yay! So we did do this long-term deployment. It was basically September through December of last year. We deployed this robot, average about 3 days a week for 14 weeks. And so there was a lot of work to actually get this going in terms of setting up a space where the robot could exist. You can see it be under construction there. It's got acoustic tiles on the roof. It's got an acoustic backdrop that also helped fix the lighting conditions, because the place where the robot was put is in this atrium with a glass roof. So that obviously wasn't good for the vision system if we didn't control things a bit. So there's a lot of low-level logistical work of getting this to happen, including we had funny situations like this was an email that was sent early in the process about the system was run on a laptop that was in a locked cabinet, and the person with the key to the cabinet was off sick that day. So there was some email traffic on the list saying, how can we turn it on? And somebody finally sent an email saying, you can try to switch the computer on through one of the holes of the cabinet with a long stick, 30 centimeters, for instance. So essentially, the people in the mall were poking sticks through the holes in the cabinet to try to hit the on switch on the laptop. So things you don't think about when you're doing one of these long-term deployments. And here's what they ended up using, a broom. And it did actually work, and we did actually run the robot that day. But stuff you don't think about when you are trying to do these long-term deployments. So the details of what did we actually deploy. So as I said, we had state-of-the-art components for audio-visual sensing, for social signal processing, for interaction management, and for perspective taking and navigation. And what was actually deployed, so the robot, when it was deployed, it could chat to people. It could chat about the weather and about movies. There was a quiz that wasn't heavily used, but it could do sort of a quiz game about what was in the mall. And it could also, and this is kind of the main thing that people sort of wanted this robot to do, was it had a 3D map of the mall, and it was able to tell you from where you were how to get to any other shop in the mall, either by just describing it or by describing it and actually using its localization information and doing some perspective taking and pointing in the correct direction for you to go. And the paper that I've listed here does give us a description of the system. I've listed it here as Foster et al. It's actually Foster and 29 other people. This was a huge, huge team effort getting this thing working. So this is all the other people that were involved in getting the system into the mall and that were involved in that paper. So it was a big deal. I won't show, if you want to find out more details about the components of the system, I'd encourage you to look up that paper, and then each section of that paper gives links to the work done by each partner, and you can find out much more about, for example, the audio-visual sensing that was done by EDIAP Research Institute in Switzerland. They did some really great stuff on face tracking, gaze tracking. So that's the work that they did. The work we did on it was social signal processing, so trying to both recognize the stuff, basically what I just described on James, in terms of here's the low-level sensor data, try to infer which of these people do we actually want to interact with, and also on the output side to control the behavior of the robot to make sure, the interaction manager might say, just say this, here's what to say, but we want to do, and, exactly what words should we use and exactly how should the robot move its body while it's saying it. And we did experiment with doing some fancier versions of how should the robot move while it was talking. So if you've seen Pepper before, you've seen that if you just give it some words to say, it'll choose some behaviors based on those words and in this, using this mechanism called animated speech. So here, for example, is a random sentence with positive sentiment, and here's what the animated speech would have chosen for that sentence.
I wouldn't be able to make it without your help.
And then with the system that we implemented, we did some extra work to both look at the sentiment, analyze the sentiment of the words, and also to do a more fluid way of choosing from a richer set of gestures based on that sentiment. And also in this video, you'll also hear we used a set of validated non-speech sounds as well as the actual words. And this is a robot. It will do some gestures that reflect the fact that this is a positive sentence, and it will also make a sound at the end that reflects that there's positive sentiment in this sentence.
I wouldn't be able to make it without your help.
So that was a happy sound. I'll just show you one more example of...
I wouldn't be able to...
Stop, next slide. So here's one example with a sentence with negative sentiment. I'll just show you the NVB, the fancy version of this, just to give you more of an idea about how Pepper moves and what sort of noises it makes.
I've just been a little depressed lately.
So we did... As it turned out, we weren't able to actually deploy these sounds in the mall system. It wasn't quite robust enough to run in the 14-week deployment, but we are doing a user study quite soon on how do people respond to these fancier gestures and the sounds compared to the basic animated speech. And if you want to find out more about this work, the paper that's linked on... No. This paper was presented at Roman last year. It's a short paper sort of describing how things work, and hopefully we'll have a paper coming out later on sort of actually describing the results of the experiment. Stop playing. So that's a social signal processing bit in Mummer. Then the bit, so the analog of the stuff that Ron described on James was done actually by Heriot-Watt University as well, but by a different group at Heriot-Watt University led by Oliver Lemon, who basically implemented the whole conversational interaction. So based on what the user said and did, it should choose what to do next. And this was using a very complicated architecture, which again, if you look at some of the recent papers from Oliver's group, it involves a whole selection of bots. So a whole ensemble of different bots, each of which would know how to respond to one particular type of query. So there was a weather bot, there was a navigation bot, there was a quiz bot, there was a chat about movies bot. And then you say something, and all of those bots would fire, and it would choose the correct answer, looking at all of those. And actually, and then it would generate that output, and it would continue. And I don't have anywhere the time to get into the details of this, but if you look at Oliver's papers, so this is how the interaction management was done in the Mummer system that was deployed. And then the last big technical component was done by Rachid Alami's group at LAS CNRS in France. And this involved localization and perspective taking and moving around. So this involved the robots having a 3D map of the mall and being able to know exactly, localize itself exactly in that map. So that if somebody said, can you tell me how to get to the toilets, it would know, it knows where you are, it knows where it is, it knows what you could see from your perspective, so it can know exactly how to point correctly at the right direction to give you good directions to get to any place in the mall. So that's another big technical component that was run in the Mummer system. And here is a sample interaction with the deployed system. This is, and you'll see sort of warts and all. The interaction eventually got to where it was supposed to go. This is somebody asking for directions to, I think, a shoemaker. And it's in Finnish because the shopping mall was in Finland, but there are English subtitles. So I'll just let this play and you can see how this actually worked in practice.
Missä on suutari?
Okei.
Missä?
Olen pahoillani. Se ei taida onnistua. Kuules, mitä olet suunnitellut tekeväsi ensi viikonloppuna?
Missä on suutari?
Okei. Tarkoitatko suutari?
Kyllä.
Okei. Katso, suutari, se on tällä suunnalla. Nyt kerron sinulle reitin. Tässä suunnassa mene läpi kulkuun läpi. Mene sitten vain käytävän loppuun. Sieltä näet heti paikan suutari. Ymmärsitkö?
Ehkä joo.
Mikä muuten on ollut sinun päiväsi kohokohta tähän mennessä?
Moi moi.
Hienoa loppupäivää sinulle.
So that's kind of what the system looked like, and you can see it didn't do the greatest job initially of understanding her, but you could see that perspective taking thing that I was talking about in terms of, so the robot turned itself very precisely and pointed in a certain direction that said, if you go down, go around that corner, then you'll see the shoemaker straight away. So that's kind of what the interactions with this robot kind of looked like in practice. And so, summary, we're still analyzing. This deployment just finished at the end of last year, and so this, as you can imagine, there is a lot of data. So we're still figuring out how did this actually work out. We estimate there were between 40 and 100 encounters per day. At least half of them were encounters with a child, because often when a family sees a robot like this in a public space, they'll kind of shove their kid forward and say, yeah, you talk to the robot. People aren't maybe interested in talking to the robot themselves. And obviously there was a whole lot of logistics in terms of making this work. And our Slack channel had, I don't know, hundreds and thousands of messages among people trying to make this logistically work. And at the start of the 14 weeks, we did find that the system would break down fairly often, and someone would need to reboot one or many components multiple times a day. At the end, things worked quite a bit better. We would still get messages, but there would be messages saying things like, the robot said something weird, or it didn't understand this correctly in Finnish, as opposed to robot isn't responding and it's crashed again. So it was still, so I think that by the end, things were working about as well as they could possibly have worked with this robot, with this system, in this incredibly difficult language that we ended up choosing to interact in. So that's what we did in Mummer, and as I said, that project has literally just finished. We had the final review meeting for that about a month ago. So we're still kind of writing up and analyzing. I expect to see multiple papers about this deployment over the next sort of year or so. We don't really have much yet because it's still a massive amount of data to analyze and write up. In terms of lessons learned from actually doing this thing, though, some things we learned from trying to put the robot into this space. Because the way it worked, it was in the shopping mall. We did have somebody on site, but she was an employee of the shopping mall. She wasn't technical. So we really had to, we had these grand ideas for what the robot might be able to do and features it could do, but we needed things that could really work with somebody maybe remotely doing things over SSH, but nobody physically on site who actually had the technical knowledge to debug anything. So we had to really sort of cut down our ambition a bit to make it actually work. And it took a huge amount of time and effort, both on-site and remote. Every day that the robot was in the mall, there was one member of the technical team whose job it was to be online the whole time, starting and stopping and responding to queries. So the robot could never be left completely alone. There was somebody physically there with it in the mall, and there was somebody there virtually, remotely, managing the robot the whole time. It was not something that was, it was autonomous in one sense, but it needed a lot of babysitting. We did find that it was hard to do this user study in the sense that we're trying to do this in the wild with people who just walk up, but then that means it's hard to do a user study in the way that you normally do a user study with questionnaires and demographics and things, because people would just want to walk away. Also, you saw the home base that we ended up needing to build with to help get the audio and the video to work as well as possible in terms of there was an acoustic backdrop, there were acoustic tiles on the roof, which also provided some more consistency of light for the vision system. We couldn't just put it in the mall and let it go. Turns out that using Finnish, doing this in Finland, was a really, really huge challenge that we hadn't expected in terms of Finnish is a beautiful language and a wonderful language, but it's really different than any language that anybody else in the project spoke. And it turns out that just using Google Translate in the loop with Finnish does not work very well because Finnish is so weird. So we had to have a lot of extra help with the actual Finnish side of things that we didn't sort of expect in the moment. And the one thing you sort of saw in that video as well is that we were pretty good at detecting engagement. We were pretty good at finding a person to talk to. What we weren't so good at was figuring out when the person wanted to stop talking to us, because the robot would just kind of want to chat forever. And there were some people who kind of ended up getting almost trapped in a conversation because they were too polite to just walk away, but the robot kept just asking, so what are you doing this weekend? And so we need to have a better mechanism, not just for engaging people in the world, but also for detecting and managing and appropriately dealing with disengaging. Because it's not like James, where once you get your drink, you're probably done. This is a robot you could chat to potentially forever. So that's another lesson learned from this, is you need to sort of think about engagement and disengagement when you're putting robots into this sort of space. I'll actually skip over these. This is another project that I've been involved in a bit, involving a social robot to help adults with autism practice their workplace-related social skills. And I will make these slides available. You can take a look at the reference papers. But the thing I actually want to talk about is this brand new project that Ron and I are both involved in. So Mummer just finished a little over a month ago. This project also just started a couple months ago. So we're really in just the very beginning stages of this project. But I just sort of want to talk about the use case and talk about what we're planning to do here, because it's going to bring together the stuff that Ron talked about before with James and the stuff that I've been talking about till now into an exciting new domain, which is about, at the moment, the name of this project is Using AI-Enhanced Social Robots to Improve Children's Healthcare Experiences. And I've been trying to think of a better name for this project. And so, in the context of children's healthcare experiences, the specific thing we're trying to help children deal with is pain. But then the only name that I can think of for this project is PainBot, which is obviously exactly the wrong sort of mental model to have. So still trying to think of a good name for this project, because we don't want people to have a mental image like this. We want to have people have a mental image like this, of a happy robot that helps children to deal with and go through these painful things that have to happen to them in the hospital. So this project right now has a very long name. We'll hopefully come up with a shorter name that's not PainBot soon. And because this project has only just started, I don't have any results or any architecture diagrams really to show you. What I just want to talk about is the overall plan for this project and what we're working on. And so the first thing, the part of this project name, is that we're looking at children's healthcare experiences. And this is particularly, obviously, you can't avoid that children experience pain and distress if they're in the hospital. The specific thing we're looking at is children in the emergency room who have to get blood drawn, which is a painful and kind of prolonged process. And if children experience, pain and distress regularly, then this has sort of negative short-term consequences for their experience in the hospital. But also, especially for children who have to visit hospitals repeatedly, it has long-term consequences in terms of needle phobia and things like that can develop if they continually have negative experiences in hospital. And so some state-of-the-art interventions for children, for helping children deal with this are actually, literally trying to distract them. This is state-of-the-art medicine, is how can you best distract children that are having this stuff done to them. And also other things to do with cognitive behavioral therapy and other ways to help them deal with it. And there has been work on a range of technology that people have used to deliver these kind of interventions in this kind of healthcare context. So giving kids books, giving kids games, giving kids virtual reality headsets to go into a VR world, using apps on smartphones or tablets. And there has been some work on using social robots in this context as well, but not really. I'll talk a bit later about what has and hasn't been done with those robots at this point and why we still think there's a space for us to try to do something slightly different. So that's the core of this project is dealing with children's healthcare experiences. And we want to use social robots for this. And this project, unlike the other ones I've been talking about mostly up till now, falls into the area of what's been called socially assistive robots. So not just robots that are meant to be be a bartender, be a guide in a mall, but robots whose goal is actually to create a close and effective interaction with human partners, to give them assistance and to make measurable progress in some specific area of life. So the autism project I just skipped over, for example, would fall into the socially assistive robots category, and so does this one. And people have used socially assistive robots, for example, in healthcare applications, such as helping people with dementia or just elderly care in general, even if it's not a dementia situation. In the context of autism, there's been a lot of work on using social robotics, especially for children with autism, for all pieces of the autism sort of treatment spectrum. So diagnosis and intervention and therapy. So that's one place where socially assistive robots have been really big. And there have been some studies, limited studies, but they have been done in terms of trying to use socially assistive robots for reducing clinical pain. And these studies, they have shown promising results, but if you look at them, they've been quite limited by the technology in the sense that all of these studies have basically been Wizard of Oz studies, completely puppeted, teleoperated robots. And a lot of the studies as well haven't involved all the stakeholders in the design of what the robot should actually do from the beginning. So it's maybe instead of involving all the parents and the healthcare providers and the children in the design of what should the robot do, it's kind of here's a robot. Here are the behaviors you can have. Someone with a tablet is pushing buttons on a wizard interface to decide what to do. It still seems like they could be a useful technique, but the results are kind of limited up to this point because of the way they've actually been used. So this is where the next part of this project comes in, is we're not just using social robots in this context. We're using AI-enhanced social robots in this. So the goal here is to make the robot more autonomous, make it able, like in James, like in Mummer, to detect the state of the people it's interacting with, choose appropriate behavior and response, and adapt on the fly, as Ron was saying at the end of his talk, in terms of you plan, but you're planning in a noisy domain full of children. Probably the state of the world isn't what you thought the state of the world was going to be. So you need to be able to choose behavior, constantly be detecting the state and adapting your behavior to that state without there having to be a wizard in another room pushing a button on a tablet. So in this project, we're going to do a series of co-design and usability studies in 2 children's hospitals in Canada to work with, as I said, all the various stakeholders. So children in this setting and their parents and the healthcare providers and probably child life specialists whose job is to sort of play with children in hospitals. That's initially to determine what behaviors the robot should even include at all and what states we want to sense, and later on to do some usability testing of the system as it's happening, as it's ready to sort of see, is it actually responding appropriately, is it behaving the way we want it to, before we come to the last bit of the project, which is we want to use these to improve children's healthcare experiences. And the way we're going to do this is actually through a clinical trial, like an actual real medical grade clinical trial at, again, these 2 children's hospitals in Canada. So we will take the final version of the system and we'll deploy it in these 2 hospitals, and we'll compare through a range of standard measures, comparing patient-reported distress and pain when the robot is present to the standard care that they normally deliver in these contexts to children in this situation. And this is especially when IVs are being inserted to take blood in the emergency room. It's that specific context. And so we're going to use, there are standard measurements for computing distress and pain, and we will use those. And a separate thing that's also happening in this project, in addition to the clinical trial, is over the whole project. Kind of an overarching goal is not just let's build this thing, let's put it out there, let's see if it works, but also to understand sort of the ethics of how to appropriately do this, because we are kind of leveraging this thing that I talked about at the start, that humans are really social and they want to be social, and children especially will want to be friends with the robots, will think that it's their friend. What is a responsible way to actually characterize a robot? What is the appropriate way to deploy one of these robots for these children in this very vulnerable situation, in a way that we're not that we're doing it in an ethically appropriate way, and we're not misusing that sort of social wiring in their brains for evil, basically. So we have a separate strand of work in the project, not only building the robot, but also considering the wider societal context that the robot's going to be placed in. And as I said, this project literally started 1.5 months ago, and everyone is in lockdown because of coronavirus, so we don't have many results as such to talk about yet, but this is a really exciting direction, and this is actually, so Ron and I are both involved in this, so I'm going to be doing the social signal processing on this as I did. So I talked to social signal recognition on James, social signal generation on Mummer. Those 2 bits of the project are the stuff I'm going to be mainly leading, and Ron is going to be doing the epistemic planning side of things, so choosing actions and monitoring the situation and replanning and dealing with error situations from the AI side. So we'll be defining the behavior of the robot, which then these Canadians are going to then deploy in their hospitals. So watch this space for that project, basically. So to summarize my bit of this lecture, humans really are inherently social creatures and want to interact socially with pretty much everything. And so it's important and useful to, people are going to want to be socially interactive with robots. So we can't stop them from doing that. So we should be able to detect the social states people have and respond appropriately. And there's both sort of practical issues to do with what appropriately means, and there's also ethical issues in terms of what's really appropriate. Do we not want to mislead people about what the robot actually can do? And so I'll give an example. So I talked about James, and you can look at the slides later to find a bit more about Socorro, which are lab-based studies. And then we've got but the more exciting thing for me is to not do so much in the lab, but to try to put robots out in the real world where real people can interact with them in a real setting. And both Mummer, which just finished, and this new Canadian project, which is just starting, are actually about putting robots into real world settings. And one last thing I want to mention, first of all, here's the web pages for the various projects. Not only does the new project not have a good name yet, it also doesn't have a good website yet, but that's a link to the proposal. And obviously, I've got a lot of collaborators here across all these projects. I do want to mention that Glasgow has what's called a Center for Doctoral Training, which is basically provides 4-year funded PhD programs in the general area of socially intelligent artificial agents. So if any of you who are listening to this lecture are possibly interested in doing a PhD in Glasgow in an area, anything that falls under the broad heading of socially intelligent artificial agents, I would encourage you to look at the website. I think there will still be another chance for students to apply for PhD starting this autumn, or if that doesn't fit your timeline, there'll definitely be a chance to apply for PhD starting next autumn. So if I would encourage you to look at the website, look at the list of projects. If this is something that you are interested in doing, you can also email me to find out more about it. And that's it for me. There's my contact details again. I know that we're basically at the 2-hour mark, but if anyone has any specific questions, feel free to put them in the chat. Otherwise, okay. So thanks everyone for listening for the last couple hours to Ron and me talking about this stuff. And as I said, we're going to send our slides to Luca, and I think he'll make them available to you. So if there's anything you want to follow up, if you want to ask us any more questions about any projects, you'll be able to find the links to all the various papers that we mentioned in those slides. And hope that I get to come back to Rome again sometime soon because I really enjoyed my time there before. But thanks, Luca, for giving us a chance to give this lecture, even if remotely. Can I spend a few words about difficulties in evaluating performance of systems, in particular social robotics experiments? It was really hard. Yeah, I didn't put any of that into this talk because there wasn't room, Luca. But it's hard. That's a whole separate. I don't think I can say anything about that right now, but I can add those slides back into the slides that I send you. How about that, Luca? And then there will be some additional information in my slides about evaluation that students can read. At that point, I think that's probably the easiest thing to do right now. Okay. So otherwise, I think I will shut this down. It's weird because there's a delay between the chat and what I'm here. So I'll wait another 30 seconds, and if I don't see anything else, then I'm going to shut this down at this point. Thanks again for listening.